Welcome back to rational functions and oblique asymptotes, part 2. I'm just going to summarize what we've done so far, and what we were looking at is some kind of a rational function that has f of x over g of x, and first thing you want to do is make sure that it is in fact oblique. And the way we know that is this top guy has to be 1 degree more than the bottom function. Okay, so if you see the top function is 1 degree more than the bottom function, we go, yes, that is oblique. Okay, so that's the first thing you want to make sure. And then what did we want to do? Well, what we're doing is we would process this through long division, and if you can, use synthetic division because it's faster. So we're essentially dividing the g of x into f of x, and then that's going to produce some sort of a quotient and a remainder, right? So that's what we're going to do, and probably we would use synthetic division, but ultimately what we're doing is we're creating a new version of this rational function. So instead of thinking of it as f of x divided by g of x, we come up with this new form, which is the quotient of x plus, and then we had this kind of a funny little fraction over here where we would put the remainder on top, and g of x, our divisor, on the bottom. Now, hopefully we look at this and we recognize that as x becomes a larger and larger number, or in the case of negatives, a smaller and smaller, like -1,000,000 or -1,000,000,000, hopefully we see that this gets so tiny we can treat it as if it equals 0. So in essence, this becomes the oblique asymptotes equation. So we can look at it and say, yep, there it is. Whatever this function happens to be, that is our answer. That's the equation of the oblique asymptote. So now, before we do an example, I wanted to make sure we're actually clear with a graph. What would an oblique asymptote kind of look like? So I'm just going to draw you a kind of rough picture here. So suppose we had some sort of function, and I'm just going to put a grid here. So maybe it looks something like this. There's our grid. And suppose we had some kind of function, and it turns out we worked out an oblique asymptote maybe goes like this. Okay. Let's just say we work this out. Whoops. It's supposed to be a nice straight line. But anyway, let's say this was the equation of the oblique asymptote. What does that actually even mean? Well, like any of the horizontal type of asymptotes, it doesn't necessarily mean anything around the origin. But what it does mean is that maybe our graph does something like this. Maybe it comes roaring up and does something like this, and as it settles down, it tries to approach that line, that dotted line, right? That's the idea of an asymptote. And then whatever else it does around here, who knows? I mean, maybe it goes roaring down like this and loops up like this, and then maybe down here does the same sort of thing. Okay? As we go further and further to the left, our function is approaching this asymptote. So that's what an oblique asymptote can look like. Doesn't have to have a positive slope, could have a negative slope, whatever the case may be. So I think we're ready for our example. And here's what our function looks like. So f of x is made up of 5x squared minus 9, all divided by x plus 2. So I can see that on the top it is a second degree polynomial, and on the bottom it is a first degree. So that means yes to that being an oblique asymptote. So yep, it's passed this little analysis. Now I'm going to go straight into the division, and I can see, oh, that's a binomial with no number in front of the x, so I'm going to use synthetic division because it's faster. So we're dividing this by x plus 2, which means plug in negative 2. Then we have 5 in front of the x squared, no x's, and negative 9. Bring down the 5, and away we go. 5 times negative 2 is negative 10. Add them up, and we get negative 10. Negative 10 times negative 2 is 20. So add those up, and we get 11. Now what this means is, essentially, our function can be rewritten in the following form. This is our quotient right here, so that's 5x's minus 10. And then we're going to add our remainder divided by our divisor of x plus 2. So when we look at this now, it's pretty obvious. You got this constant 11 on the top, but x is going to theoretically become big numbers, like a billion. 11 divided by 1,000,002 is very, very small, and we would consider this to be so small we count it as 0. So here is what the function tries to approach as it goes to extremes. It tries to approach this line of y equals 5x minus 10. So this is our oblique asymptote. Okay? And that concludes our look at asymptotes for now. We'll see you later.